These slides will cover how to balance nuclear equations. So our objectives: write and balance nuclear equations. Nuclear equations involve changes in atomic number, mass number, and energy level. So we're going to follow these two rules. The sum of mass numbers, A, of the reactants is equal to the sum of mass numbers of the products. The sum of atomic numbers, Z, of the reactants is equal to the sum of atomic numbers of the products. Before we try to balance nuclear equations, we are going to review atomic symbols. Atomic symbols use the following format. X is the element symbol associated with a specific number of protons. So for example, if we have helium, we give it as He. 2 protons is He. A is the atomic mass number, which is the number of protons plus the number of neutrons in the nucleus. Z is the atomic number of the element, i.e. the number of protons. Often, Z is actually left out of this formalism entirely because Z is usually associated with the element via the periodic table. For our purposes right now, we're going to refamiliarize ourselves with this, and we will leave it on for these things. So an example of an atomic symbol, we have carbon-14 as an isotope, which is given by the C for carbon, 14 for the atomic mass, and 6 for the number of protons. So we have a number of steps for balancing nuclear equations. 1, we will write all the elements and particles using isotope notation. So mass numbers in the superscripts, atomic numbers in the subscripts, and we use the element symbol for the X. Step 2, make sure the mass numbers sum to the same amount on both sides of the equation. Step 3, atomic numbers should sum to the same amount on both sides of the equation. And step 4, identify the missing element or particles. So step 4, steps 2, and 3 kind of iterate on each other. Step 5, construct the balanced nuclear equation. Write the nuclear decay equation for carbon-14 decaying into nitrogen-14. Let's follow our steps. So we're first going to write the elements and particles using isotope notation. So we've got our carbon-14 and our nitrogen-14. And we are going to then, step 2, make the sum of the mass numbers the same amount on both sides of the equation. So I'm just going to take that 14 and put it equal to 14 plus x, which when I solve for x, that's 0. Not a surprise. Step 3, atomic numbers should sum to the same amount on both sides of the equation. So this is where it's handy to include the Z in your isotopic symbols, because if you don't, this step is difficult. Here we have 6 equals to 7 plus x, which if we solve, x equals -1. So now, step 4, we're going to identify the missing element or particles. We take a look at the list of possible decay particles, and we notice that we have a mass of 0, so that makes it either a positron or beta particle. But we've got a -1 for the atomic number, so that definitely makes us a beta particle. And we could write it in 2 ways, but I chose to use the one where we represent it as an electron. And then I'm going to put everything together. I'm going to construct the balanced nuclear equation. So we have carbon-14 going to nitrogen-14 via a beta emission. Let's try doing something a different way. So we're going to write the nuclear equation for thorium-232 decaying by alpha emission. So we start with step 1 and we put our atomic symbols in. Okay, so now we need to figure out what we're missing. And we're going to do that by step 2, making sure the mass numbers sum to the same amount on both sides. So in this case, we have 232 equals x plus 4. X then becomes 232 minus 4. X is 228. So this is another big particle. Step 3, the atomic numbers should sum to the same amount on both sides. So when we do that, we have 90 equals to 2 plus x. X equals 88. All right. we have 228 for our atomic number. We have 88 for our our atomic mass number. We have 88 for our atomic number. If we go to the periodic table and look that up, our missing particle is radon. Radon has 88 protons. All right, so now we plug everything back into the equation and we write it out. So you can be given what it's decaying by. You can be given the product of a decay of one type. There's lots of different ways that we can do the thing, but what we're always doing is trying to identify what's missing in the equation, and we're balancing so that our atomic numbers balance and our mass numbers balance. Let's summarize. Nuclear equations involve charges or changes in atomic number, mass number, or energy level. We're going to follow two rules. We're going to sum mass numbers in the reactants equals to the sum of mass numbers in the products. We're going to say that the sum of atomic numbers of the reactants is equal to the sum of the atomic numbers of the products. So we can have nuclear synthesis equations where we're taking two things, doing fission, and making a new, larger number. Just in case you're wondering why I said that thing. We have a 5-step process for determining what our stuff is. We write out the elements or particles that we're given using the isotope notation. We make sure that the mass numbers sum to the same amount on both sides of the equation. Then we make sure the atomic numbers sum to the same amount on both sides of the equation. And from there, we can identify our missing element or particles. And finally, we construct our balanced nuclear equation. And I've given the table of the symbols that we use for the various types of nuclear decay so that hopefully we can make those connections.